Welcome to Engineering Studio with Dr. Mohammed Tahir. In this video, we are going to have revision of some basic concept like types of load, their transfer mechanism, bending stresses, shear, torsion, moment of inertia or second moment of area, buckling. So these concepts will be actually utilized while designing a structure. So if you have a clear understanding of these concepts, so it will help you to decide the shape of the structure, decide the shape of the section, and it will help to economize your structure. First of all, type of load, dead load. So it is a load which retains its magnitude as well as point of application throughout the life of structure, and it is denoted by D. So this load usually is the self weight of the structure as well as the floor finishes and if there is some permanent feature. So this is estimated by multiplying the volume of the member with the standard density. For example, if we want to calculate the dead load of a slab, so what we will do, we will multiply it with the dimensions, length, width and depth or thickness of the slab with the density of the material. So this load constitutes a bigger part of the total load. So the proportion of this dead load is highest among all the applied loads, or we can say in the gravity loads. Next is live load, a load which changes its magnitude as well as point of application. That load is termed as live load. So the load of persons occupying that structure is normally the live load, or movable things, movable furniture or some other material. So in case of bridges, the live load is the load of moving vehicles. So in the design specifications of AISC minimum design loads, the value for different occupancy category are given for live loads. For example, for private apartments, school classrooms, the minimum live load is 200 kg per meter square. For offices, it is 250 kg per meter square. So from this table, we can select the appropriate value of live load based on the occupancy. Next is imposed or superimposed load. So all the externally applied load except the self weight are termed as superimposed load. It may be live load, it may be earthquake load, wind load. So these loads are termed as superimposed load. The next term is service load. So it is the maximum intensity and load expected during the life of structure depending upon the certain probability of occurrence. It is termed as service load. So in case of service load, we do not apply any additional factor of safety. So factor load, so if we apply a factor of safety on the service loads, this will be termed as a factored load. Next is mechanism of load transfer. So the gravity load passes from top to bottom through all the member of the structure. So the load of the slab will go to the beam, and the load of beam and all the load that have been supported by the beam will go to the column, and then all the load supported by the column as well as the self weight of the column will transfer to the footing, and then this footing will transfer the load to the soil. So this is the transfer mechanism. And the term support is actually a relative term. For example, for beam, the columns are the supports for beam, and similarly beam act as a support for the slab. So the next term or the next concept is equilibrium. So a body which is not moving is said to be in the state of equilibrium. So there are two types of equilibrium: stable equilibrium and unstable equilibrium. So a body will be in a state of stable equilibrium when any small movement increases its potential energy so that when it is released, it tends to resume its original position. For example, In this case, we have a bowl and a ball is placed inside. So if we displace this ball from its equilibrium position and we release it, so after some oscillation it will come to rest at its original position. So this is a stable equilibrium, that it has again gained the equilibrium state. Similarly, if we have a simply supported beam and apply a load over here, so it will deflect in the downward direction. It will be displaced. But when we will remove that load, so it will come into its original position. The next is unstable equilibrium. If a body is said to be in the state of unstable equilibrium, if following any small movement, it tends to move away from its original position and it will not resume its original state of equilibrium. For example, again we have a ball, but it is turned upright and we place a ball at its peak, and for example it is at rest, and if we apply a small force and try to move it, so it will fall down. It will not come back at its original position. So this is termed as unstable equilibrium. Similarly, in this case, if we have a roller and we have placed it on a marker, and if we just apply some load over here in this direction or in this direction, so it will move away from its original position and it will not come back to its original state of equilibrium. So in case if a body is in a state of equilibrium, so all the forces, the sum of all the forces will be equal to 0. Similarly, a body to be in equilibrium, the sum of all the moments acting on the body will also be 0. So all the forces acting on the body as well as all the moments acting on the body at any point will be equal to 0. So summation F is equal to 0 as well as summation M is equal to 0. These two conditions will be fulfilled if a body is in a equilibrium. So here we have a model demonstration for the equilibrium. So here in this case, there is a wooden piece. So if we try to balance this wooden piece in this way alone, it will not be balanced. It will fall down in this direction. But if we put this bottle inside it, the neck of the bottle, so in that case, it will be stable at this point. So the stability of this is because the moment because of the weight of this bottle as well as the moment because of the weight of this wooden sheet about this point is 0. So this moment in this direction as well as moment in this direction both are equal. So this bottle will not fall down, it will not rotate. So this is in state of equilibrium. The second model is, this is a concept which is used in the magnetic levitation train. So if we place these ends of magnet over the same end of the magnet, so in that case a repulsive force will act on these two ends and this dumbbell will stay in its suspended position. So visibly there is no contact between these two surfaces and no force is acting on this dumbbell, but in actual there is a force because of the magnets which is holding the dumbbell at its position. So in that case it will be in equilibrium. So we can use the concept of equilibrium for the design of structure. For example, for this walk-through gate, this barrier, if we do not place a counterbalance at the back end and if try to open this, it will be very difficult to open this barrier anytime. But if we apply a counterweight at the back side and we bring it into equilibrium, that the moment because of this counterweight as well as the moment because of the weight of this barrier, these moments are equal, so in that case it will stay at its original position. And if we want to open it we need a just small thrust or small force to open this barrier. So this concept is used to design these barriers. So here in this figure we have a bridge, movable bridge. So if we want to lift the deck of this bridge, it will be very difficult. So we need a heavy machinery, heavy equipment to lift this deck slab. But if we use the concept of equilibrium and apply a counterweight at the back side and attach this deck slab on this side, so here we have a pivot point. So the counterweight will apply a moment in this direction and the weight of this deck slab will apply a moment in this direction. So if we design this counterweight in such a way that the moment because of this counterweight as well as the weight of this deck slab are same, then we can easily lift this deck slab manually. A single person can lift this deck slab. So the next is how we can draw bending moment and shear force diagram. So for example, if we have a simply supported beam and a point load is acting at a distance A from the support A and at a distance B from the support B. So in that case, if we take section before this load P, so we will have reaction RA over here, and the magnitude of this reaction RA will be equal to P times B over L. Similarly, the amount of reaction at point B will be equal to P times A over L. So based on these two reactions, we can easily draw the shear force diagram. Here we have a reaction RA, then up to this equal to PB over L, and up to P point we don't have any force, so it will remain constant, and then we will subtract this P from this PB over L and we will get the value equal to PA over L, and again up to this support there is no force, so here PA over L, and this shear force diagram will close. So in this way, based on this reaction, we can draw the shear force diagram. Similarly, the bending moment, to draw the bending moment we can find the area of this shear force diagram. We can accumulate that area. At this point the moment will be 0, and up to this point we can add the area, and the maximum ordinate will become PAB over L. So PB over L multiplied by this A, so it will become PB over L times A, PAB over L. So the maximum moment will be equal to P times A times B divided by L. And as the shear force diagram is a constant, so the bending moment diagram will be a linear first degree curve. Similarly, if a uniformly distributed load is acting on the beam, in that case the shear, we can find the reactions as Q times L divided by 2. So it will be QL by 2, this reaction, and this will be QL by 2. And shear force here will be QL by 2, here will also QL by 2, and their variation will be linear. So here the load is constant, so the shear force will be linear, and the bending moment diagram will be a second degree curve, and the maximum ordinate will be QL square by 8. Similarly, we can see the comparison between load, shear and bending moment diagram. If load is 0 or a constant load is acting, in that case shear force will be constant and its degree will be 0, and the bending moment diagram will be linear with 1 degree. And if a constant load is acting, in that case the shear force diagram will be linear and the bending moment diagram will be parabolic. And if the load is linear, then shear force will be parabolic and the moment will be cubic or third degree curve. The next concept is center of mass or center of gravity. The center of gravity of a body is the point at which the body is balanced, or the point through which the weight of the body is acting. So it is actually the point at which we can balance the body. So the location of center of gravity of a body coincide with the center of mass if the dimension of the body are much smaller than those of Earth. So all the structural members are the shapes on the Earth. Their dimension is very small as compared to the dimensions of Earth. So we can say that their center of mass as well as the center of gravity coincides with each other. So when the density of a body is uniform throughout, the center of mass and the centroid of the body are at the same point. The centroid as well as the center of mass will be same if the thickness as well as the density of the member is same. The center of mass or center of gravity is the point about which we can balance the member or balance the body. So here we have our demonstration. We can balance this fork and spoon at the edge of the glass. This is because the center of mass of these two is lying over here. So we can balance it at this point. Similar demonstration is in this case. We can balance these forks with a cork and a needle at the edge of the bottle. So again, this is because the center of mass of this assembly is acting at the end of this needle. So there is very important information related to center of mass which can be used for the design of structure, which is if the center of mass of a body is not positioned above the area over which it is supported, the body will topple over. So if, for example, this is a structure, here is its center of mass, it is acting over here, and this is its supported area. So as the line of action of this center of mass as the weight is passing through this supported area, so it will be stable. But if we turn it like this, and if this center of mass or the line of action of this weight is out of this area which is supporting this structure, so in that case this structure will topple over. The lower the center of mass of a body, the lower or the more stable will be the body. And if larger the supporting area of the body, more stable will be the body. So if we increase the supporting area, so we can make the structure stable, as well as if we lower its mass center, then again by lowering the mass center we can also make it stable. So here we have demonstration for these two concepts or for these 2 points. For example, we have this rectangular body, a tower, and a pyramid type structure. So at this stage their center of mass is over here and the line of action of weight is in this direction. So the center of mass in case of this rectangle is lying at the center, and in case of this pyramid it is lying at 2/3 from the top or 1/3 from the bottom. So if we rotate its base like this, so first of all this structure or this rectangular structure will fall down, this will topple over. This is because as the center of mass is high, so just with a small rotation this will come out of the supported area. So the line of action of its weight will go outside the supported area, so it will topple over. So the critical angle or the topple angle will be almost 15 degrees centigrade, 15 degree. And if we further increase its topple angle, the inclination of its base, so then this second shape will topple. This with the further increase in it, the inclination angle, this weight, the line of action of weight will go away from the supported area and this structure will fall down. So here in this case both the structure have same supported area, but the structure with higher center of mass will topple first. And if we compare these two structures, both have same height, same shape, so it means their center of mass will lie at the same height. But in case of second shape we have higher supported area. So in case of second shape, because of higher supported area, so it will topple at the later, at the higher inclination angle. So if we summarize these three models, so this model will topple first at 15-degree angle, this model will topple at 30-degree, and this will topple at about 10-degree, this is at 20-degree, and this is at 30-degree. So here the difference was the height of the center of mass, and here the difference was the supporting area. Lower the center of mass, more will be the stability of the structure. Similarly, higher the supporting area, more will be the stability of structure. So this concept of center of mass is used for the design of different structures. For example, in case of Eiffel Tower, the base of the structure is enhanced. This is to lower down the center of mass. So when the center of mass is lower, so it will not topple because of earthquake loads or wind loads. Similarly, we see this shoe rack in the market. So alone it can topple because its center of mass will lie over here and it will be away from its supporting area, so it can topple. But if we want to make it stable, we need to increase its supporting area. So now this center of mass is passing through the supporting area, so it will become stable structure. Here if we see this structure, here the line of action of the mass or the center of mass will be over here, and it is passing from the supported area, so this structure will be stable. Visually it look like that it will topple over, but it will be a stable structure because the center of mass lies over the supporting area. So the last figure, this is very interesting to understand the concept of center of mass. So in case of tower crane, if we reduce this portion, so in that case the center of mass of this whole structure, including this weight and the weight of this beam, will lie somewhere over here, and this is away from the supporting area, so this structure will topple over. So either we need to increase this base or we need to shift the center of mass. So we cannot increase the base, the supporting area, because this tower crane is placed near to the structure, so we cannot enhance its support or its foundation inside the structure. So in that case what we do, we add some counterweight at the back side. So by adding this counterweight, we have shifted the center of mass of the structure near to this tower, this vertical members, and this is passing through the supported area. So as a result, our tower crane will not topple over. And similarly, this also reduces the shift of bending moment into this vertical members. So as there is no bending moment, so no bending moment will be transferred to the foundation, and this structure will remain stable. The next concept is second moment of area. We sometimes incorrectly call it as moment of inertia. The second moment of area sometimes incorrectly called as moment of inertia. Actually, moment of inertia is I is equal to mr square, mass time the radius of, or we can say the distance from the point of rotation up to the center of the mass. But here the second moment of area is not the same as moment of inertia. It is actually the second moment of area. So second moment of area is a geometrical property of a plane cross section. So it is a geometrical property which is based on area as well as its distribution. So what it means? Further the material of a section is away from the neutral axis of the section, larger will be the second moment of area. For same cross sectional area, if we make a shape, if we arrange that area in such a way that the material is away from the neutral axis, in that case the moment of inertia or the second moment of area will be high. For example, in these two figures we have same area, but the moment of inertia, second moment of area magnitude is different. Here it is only 6.6 inch to power 4, and here it is 166.6. The reason is, in first case the material is close to the neutral axis, and in second case the material is away from the neutral axis. Just by changing the placement of or the distribution of area, we have significantly enhanced or increased the second moment of area. Therefore, the shape of a cross section will significantly affect the value of second moment of area. So if we want to change the second moment of area keeping the cross sectional area of the member same, we can change its shape. For example, for this as well as for this. For these three shapes, we have the same cross sectional area, but the second moment area will be different. The stiffness of a beam is proportional to the second moment of area. So this second moment of area actually defines the stiffness of beam. Larger the second moment of area, larger will be the stiffness of the beam. For example, if we see this figure, in the first case, the orientation of the member is like this, that the material is away from the neutral axis here. So here the I will be high, so the deflection, the rigidity of the structure will be more. The deflection will be less and the stiffness of the structure will be more. In the second case, the material is close to the neutral axis. In that case, there will be a excessive deflection in the wooden plank. So here we have a model demonstration to show how the second moment of area is affected by the shapes and it influences the stiffness of the beam. Here we have three plates we have combined in three different ways. Here we have placed it like this, and here we have placed these three plates in vertical direction, and here we have arrangement like I section or W section. So if we apply the load on the first, it will deflect excessively. This is because the moment of area of that section is very less. As a result, the stiffness will be low. In the second case, the moment of area is high and there will be very small deflection. And in third case, the moment of inertia is further increased because of changing the orientation. We have removed the material near to the neutral axis and we have shifted away from the neutral axis. As a result, the moment of inertia will increase. Second moment of area will increase and we will have a higher stiffness of the member. Similarly, we have another model just for the demonstration. If we have a card and if we try to place the book and if we try to lift the book on this card, it will be impossible. It will bend like this. If we hold it over here and try to place a book on this side, so it will bend. It will not be able to lift the book. But if we convert this card in this V shape, and then if we try to lift this book on this card, so it is possible. So this is because by changing the shape of this card, we have increased its second moment of area. As a result, the stiffness will increase. So how we can utilize this concept in the structures? So here we can see that in practically we use W section in case of beams. This is just because the W section or the I section have higher moment of area. We have reduced the material close to the neutral axis and we have placed it farther from the neutral axis. As a result, the stiffness has increased. Similarly, if we see these two figures, in that case we have removed the material near to the neutral axis, because the material near to the neutral axis will not contribute much in second moment of area. So we can remove the material near to the neutral axis and the stiffness of the structure will not be affected. So by removing or by punching these holes, it will also reduce the wind loads. So we can get dual benefit. We have reduced the wind effect as well as we have saved the material without affecting any stiffness of the member. The next is how we can calculate the second moment of area. For a simple rectangular section or regular shapes, here it is B and this is H. So the moment of inertia is equal to I is equal to BH cube over 12. So this is about its neutral axis, about its centroid. So if we want to calculate the moment of inertia about any other axis, for example at this bottom, then we need to transform this moment of inertia about this axis by using parallel axis theorem. So here this Ix dash, this one, and then we need to transform by adding area times the distance from the neutral axis up to the new axis about which we want to calculate the second moment of area. So we will add a d square to transform this section about the new axis. So for other sections like this T section, so here the neutral axis will lie over here or the centroid will lie over here. So for this rectangular section we can calculate the second moment of area just by BH cube over 12, and then we need to add the second moment of area of these two sections about this centroid. So for that we will calculate the second moment of area of this section, which is BH cube over 12, plus we will add area of that section times the distance from the centroid of this shape up to the centroid, so d square. So in this way, similarly, we will also add the same second moment of area and we will transform up to this centroid. So in this way, we can calculate the second moment of area of other shapes. For example, we can solve one example over here. We have a T section or we can say we have a I section. Here the thickness is 2 millimeter and this is 30 millimeter. This is also 30 millimeter and 2 millimeter. The thickness of web is 2 millimeter and the depth is 20 millimeter. So the second moment of area will be equal to about where the centroid will lie over here, because it is a symmetrical section about the both axes, so the second moment of area will be at the center. So the centroid will be at the half of the depth of the section. So I will be equal to for shape 1, for shape 2 and for shape 3. So shape 1 and shape 3 are same and have the equal distance from the centroid, so we can calculate for one figure and then multiply it with the 2. So for figure 1 it is 30 times 2 cube divided by 12 plus 30 times 2 times the distance from here up to the centroid. So this is 10 plus 1, it is 11 square. So we will multiply it with 2 to account for the third figure, then plus for second figure it is 2 multiplied by 20 cube over 12. Here the area is 20 times 2 times the distance between the centroid of this whole figure as well as the centroid of this second figure is same, so it will be 0 0 square. So from here we can calculate the second moment of area about the centroid of this composite shape. Similarly, we can also calculate the second moment of area for this built up section by using the parallel axis theorem.